Okay, so I left off after part A of this example number 6. I discovered that it didn't quite work to do the entire example and then get to example 7 as well, so this looks like a pretty good break point, I believe. So we were at none were born on Friday. Well, in order to do this, we have to think about the complement of being born on Friday. So not being born on Friday, that probability is the complement of being born on Friday, which is 6 and 7. So the probability that none are born on Friday, that one is equal to the probability that all are not born on Friday, right? So this probability that none are born on Friday is actually equal to the probability that three are three are on not Friday. So looking at that probability, well, that's not too hard. That's the probability that the first one isn't born on Friday. And the first person doesn't affect the second person, right? So these are independent probabilities. And so that would be times the probability that the second is not born on Friday. And then times the probability that the third person is not born on Friday. And these being independent, that's just 6/7 times 6/7 times 6/7, and that gives us 6 cubed over 7 cubed, and 7 cubed we already know is 343, and we just need to know what 6 cubed is, and I believe that is 216. And so there's our probability, and then we can certainly go in and we can find out what 216 divided by 343 is equal to, and that's 0.629738. So 0.629738, and I want to take it out to approximately there because this is where we need to round it, but you see it's going to need to round through this time. So 0.630 is the probability that we're looking for. Now moving on to part C, it says that none were born on the same day of the week. Now this is back to that same question of what's the probability that 3 randomly chosen people are all born on the same day. This is the probability that none on the same day. This one says, okay, well, the first person, they get to have any birthday they want, right? So this is really that the first person has birthday. And that is, of course, equals to just 1. And then probability that the second isn't the first person, and the probability that the third isn't the first or the second. So isn't, and then first or the second. And so that one says, okay, well, if this person is born on Wednesday, then I can't choose Wednesday, but the second person could have Thursday, Friday, Saturday, Sunday, Monday, or Tuesday, so they have 6 out of 7 choices. And then the third person, well, they can't be born on, let's say the second person was born on Tuesday, so the third person can't be born on Tuesday or Wednesday, but they still have Thursday, Friday, Saturday, Sunday, Monday to be born, so they still have 5 out of 7 possible choices to have. So this gives us a probability of 30 out of 49. And finding out what that is, 30 divided by 49, we find that probability to be 0.612. So our probability here being 0.612. Okay, now going on to our excuses for missing a test. We have a classic excuse of a missed test offered by 4 students who claim that their car had a flat tire. On the makeup test, the instructor asked the students to identify the particular tire that went flat. What's the probability that they didn't have flats and all randomly chose the same flat tire? So this is the probability that their their tires are all the same, right? Tires are all the same flat. So this first person, they can choose any tire that they want. So let's just say that the first person really did have a flat tire, and their left front tire was flat. So the probability that their left front tire went flat, it's the 1, right? And then the next person, well, they have to have the same flat tire as that person. So let me draw a little car here, right? So here's my little car, and I'll just do this for you. Okay, and so this was the first person's flat tire. So they chose that flat tire. And then the second person, they have to choose that same flat tire. And so they have a 1 in 4 chance that they choose that same flat tire. And then the second person, or third person, they also have to have that same flat. And so they choose a 1 in 4. And then the third person has a 1 in 4 probability of choosing that same flat tire. And so the probability that all 3 of them choose the same flat tire is a 1 in 4 to the third power, or a 1 in 64 chance that they are all going to have the exact same flat tire. And that is assuming that it's random choice, right? That you have this probability of getting a flat if you're randomly choosing them is just a 1 in 4 chance. So that's what we're looking at. And this is our probability is the 1 in 64, which of course 64, 1 divided by 64 is equal to a 0.0156 case, 0.0156. And again, Triola would find this to be very unusual, right? He would find it to be at least unusual because it's less than 5%. So less than that, it's unusual, and therefore he would say, I don't really believe these people because this is an unusual thing to happen if they're all going to be getting a random flat tire, unless there's something else going on here that we don't know about. So that would be how we can apply the same logic to another type of problem. All right, so next we'll be doing section 4.6, which is our counting techniques. So I'm just going to stop this video now, and I'll start another one up for the counting techniques.